Hey Geometry, welcome to lesson 16. It's called Between Figure and Within Figure Ratios. Today we're going to talk about ratios in geometry, and in my experience with standardized testing, just ACT type stuff, ratios are extremely common, and you should be able to whip through ratio problems without a ton of extra thought. So hopefully with this introduction we can give you an idea of how to do ratio problems. So ratio problems and scale factor go hand in hand. Let's look at this opening exercise and see if it can just give us an idea of how this stuff works. At a certain time of day, a 12-meter flagpole casts an 8-meter shadow. Write an equation that would allow you to find the height h of the tree that uses the length s of the tree shadow. This really means that up here there's a big old sun. Actually, it's almost like right there, only because it needs to be right in line with our shadow. Okay? It's sort of a make-believe type world where the sun is a 90-degree line with the earth, and it casts shadows that are just perfect, not taking into account any curvature or anything else. So, all right, let's get into the math of it. What we see here is I've got a triangle, and it's two similar triangles because of angle. There are my two angles that are congruent, the 90-degree one and this one, only because the triangles share this angle, and by the sun casting a shadow, we know that the 90-degree angles are equal. Let's see, we have 12 here, h, this whole thing is, I can't read that, looks like Z. Nope, S. That is a funny looking S, but that's okay. So if I draw two separate triangles, we're going to see H and S and 12 and 8. So we can set up a ratio now. The ratio can be set up many different ways, but we're going to stick with little triangle equal to big triangle. And just note, little triangle I have 12 over 8, big triangle I have h over s. So this is the ratio we're going to set up. I could also do h over 12, big side over big side, equals small side over small side. There's lots of different ways I could set it up. It doesn't matter as long as you stick with the same pattern. Actually, I'm going to rewrite that. Sorry. I did h over 12 and s over 8. I could even do 12 over h equals 8 over s. Like I said, it doesn't matter as long as you stick with the same pattern. Cool? This just said write an equation. Check. Done. Okay, example 1. So we have similar triangles here because the instructions tell us that they're similar. We can use these similar triangles to find the missing side lengths. And again, there's lots of different ways that we can work this. I could go 4 to 12 because we have A, B, C, and A prime, B prime, C prime. So A, B, let's see, A, B, C, A prime, B prime, C prime. So these are already set up in corresponding spots. Okay, those correspond, that corresponds, and this corresponds. So if I did 4 over 12 and I'm trying to find a missing side, I can set that equal to 5 over A prime, B prime. I always cross multiply because it's just how my mind works. 12 times 5 is 24, 48, 60. equals 4 times a prime b prime. If I divide both sides by 4, I get a prime b prime equals 15. So I have the scaled up triangle solved. Let's go ahead and do the other one. Let's go ahead and do 4 over 12 again. They're my two sides that are the same. And then I can do CB over 6. I'm going to cross multiply. 24 equals 12 times CB. So CB equals 2. Okay, let's look at something else. Let's try if we can try to do this problem using scale factor. If I go from triangle ABC, which we know is similar to triangle A prime, B prime, C prime, I want to know what the scale factor is. R times 4 equals 12, so R equals 3. My scale factor is 3. That means that R times CB equals 6. R is 3, CB equals 2. It works that way also. R times 5, which is AB, equals A prime B prime. So R we decided is 3. 3 times 5 is 15, which is A prime B prime. So we can solve this using scale factor also, and it's really whatever method works well in your mind. I've always used the first one that we talked about, where I just compare sides of the two triangles, but we spent a lot of time talking about scale factor the last few lessons, so I thought scale factor might work for you guys also. Here, let's try another example. In the diagram above, a large flagpole stands outside of an office building. Marquis realizes that when he looks up from the ground 60 meters away from the flagpole, the top of the flagpole and the top of the building line up. If the flagpole is 35 meters tall and Marquis is 170 meters from the building, how tall is the building? And again, this is where we sort of have a few assumptions here. Marquis is ground level, which I know isn't completely possible, but that's what we're looking at. His head he's laying on the ground, he's looking up, the top of the flagpole lines up with the top of the building. Okay, he is standing 170 meters away from the building, so we have our big triangle, but we don't know how tall the building is, and then we have our small triangle. I don't know why I drew it that way. Our small triangle, which is 60 meters away from Marquis and 35 meters tall. These are similar triangles because they are right angle on one side and they share an angle on the other side. Okay, so let's just set up our proportion, our ratio. It doesn't matter how you do it. I'm going to say 170 over 60. I just went base of the big one over base of the little one equals h over 35. Go ahead and cross multiply. 60h equals, hold on a second, 5950. Divide both sides by 60. I have h equals 99.2 meters. That reminds me, I'm not sure if I used units in our opening exercise. Make sure you write down your units when you're working these problems. Yeah. Actually, I haven't even looked at the questions yet. That is so funny. Let's go look at A. This is when I should probably erase the part of the video and re-record because I made a silly mistake. But that's all right. You guys can see my silly mistakes. A says, are the triangles in the diagram similar? Yes, we can say because we have angle-angle similarity. We had a right angle and then they share an angle. So I've got two angles. Part B, determine the height of the building using what you know about scale factors. Check. So I need to figure out the scale factor between the two triangles. I think I had the big one 170 and h, and then the little guy, what was it? 60 and 35. Let's do scale factor just between two sides. So r times scale factor times 60 equals 170. So your scale factor equals 2.83. So I should be able to do my scale factor times 35 equals h. So 2.83 times 35 equals h. Times 35, 99.2. Let's see what else we can do. Okay, C says determine the height of the building using ratios between similar figures. This is what I did in the first slide that has to do with this problem. I think I did 170 over, is it 60? I think so. Again. Yep. Equals h over 35. Cross multiply. 60h equals 5,950. Divide both sides by 60. And I got 99.2. Thank goodness. It'd be awful if I got something different, wouldn't it? Determine the height of the building using ratios within similar figures. So I'm just going to set up the small triangle equals big triangle. So in the small triangle, I would have 35 over 60, and you still have the picture in front of you. That's the small triangle, and then the big triangle would be h over 170. Now again, I can cross multiply, and everything works out the same. 60h equals 5,950. Divide both sides by 60, and I still get 99.2. 3 different ways, all the same answer. Life is grand. Okay, example 3. The following right triangles are similar. We will determine the unknown side lengths by using ratios within the first triangle. For each of the triangles below, we define the base as the horizontal length of the triangle and the height as the vertical length. Now there's a bunch of questions, so I'm going to go ahead to the next slide to answer some questions. So first of all, it says write and find the value of the ratio that compares the height to the hypotenuse of the leftmost triangle. That gives me 4 over 5, which is 0.8. Write and find the value of the ratio that compares the base to the hypotenuse of the leftmost triangle. So I have base and hypotenuse. 3 over 5, which is 0.6. And then write and find the value of the ratio that compares the height to the base of the leftmost triangle. So 4 over 3, 1.33333. Let's see what else we got. Okay, use the triangle with lengths 3, 4, 5 and triangle A to answer the following questions. Hold on a second. Okay, the first question says which ratio can be used to determine the height of triangle A. So the height is right here, which compares to this side right here, right? But they're looking for words for an answer. So the ratio that compares the height to the base of the little triangle would work. Which ratio can be used to determine the hypotenuse of triangle A? The ratio that compares the base to the hypotenuse. Would work for that one. Find the unknown lengths of triangle A. So first I can do, what did I say, height to base. 4 to 3 equals, we'll say x to 1.5. I'm labeling that x. Go ahead and cross multiply. 3x equals 6. X equals 2. So I'll go ahead and replace this with a 2. And hypotenuse. If I did base to hypotenuse, so 3 to 5 equals 1.5 to y. Let's say that's y. Go ahead and cross multiply. 3y equals 7.5. Y equals 2.5. Go ahead and replace that. Got them both. Cool. E, use the triangle with lengths 3, 4, 5 and triangle B to answer the following questions. Hold on a sec. So which ratio can be used to determine the base of triangle B? Let's see. I have the height, so that'd be the base to height. Ratio. Which ratio can be used to determine the hypotenuse? That'd be the height to hypotenuse ratio. Oops. Not sure what I was writing there. That just means here, if I have the height, and for part I, I'm trying to determine the base. So if I have the height and I'm trying to determine the base, I'm going to compare it to height and base. And part II, if I'm trying to determine the hypotenuse, I have the height, I'm looking for the hypotenuse, so I'm going to compare it to the height to hypotenuse ratio, right? Let's go ahead and try it. So we'll just say there's x and y. First of all, let's do, base to height, which would be, that was 4 over 3 when we did it the first time. 4 over 3 equals 5 over y. Okay, I did 4 over 3 is equal to 5 over y. And then I can do, I'll solve that in a second. If I'm trying to find the hypotenuse, I can do 4 over 5 base, or height to hypotenuse, is equal to 5 over x. I did 4 over 5 is equal to 5 over x. Go ahead and cross multiply. 15 equals 4y. 3.75. And then cross multiply. 25 equals 4x. 6.25. That works. And then F, use the triangle with lengths 3, 4, 5 and triangle C to answer the following questions. Hold on. Okay, which ratio can be used to determine the height of triangle C? Well, I have hypotenuse, so the hypotenuse to height ratio which ratio can be used to determine the base of triangle C? It'd be the base to hypotenuse ratio. Find the unknown lengths. Let's go ahead and label these arbitrary x and y. So I can do hypotenuse to height would be 4/5. Will give me, so I'm doing 4 over 5 is equal to y over 8. And then I can do base to hypotenuse. Base to hypotenuse, 3 over 5 equals x over 8. Okay, cross multiply. 5y equals 32. Y equals 6.4. Cross multiply. 5x equals 24. X equals 4.8. All right, explain the relationship of the ratio of the corresponding sides within a figure to the ratio of the corresponding sides within a similar figure. All that means is if I have two similar triangles, Corresponding lengths of similar figures have proportional lengths. But the ratio of two lengths within a figure is equal to the corresponding ratio of two lengths in a similar figure. Let me write that down. Okay, that's all in black. Let's look at H. How does the relationship you noted in part G allow you to determine the length of an unknown side of a triangle? Well, when you have a relationship and you know the relationship, you know the scale factor, you know the ratio, it allows you to find the length of the unknown side. It's what we did for the last 3 triangles. So since the ratios are equal, the unknown length can be found by solving this simple equation, just cross multiplying. Okay, just summarizing that. We write the ratio of corresponding sides and solve the simple proportion. And that's actually it for today. Awesome. Good work. I hope you enjoy the problem set. It's a little more calculations than we've seen in the past few lessons.